Hello, everyone. Good morning, good afternoon, and good evening, wherever you're joining us from. Welcome to this talk, Model Monitoring, What, Why, and How with Manasi. My name is Faraz. I'm your MC and the co-organizer. Just before we get started, a couple of housekeeping items. If you have any questions, uh, if you have any questions, please feel free to ask them in the chat with a Q in front, so that we can collect and address them after the talk. If you haven't already updated your profiles, please do so right now. This will help you connect with your fellow attendees. And lastly, please visit the booths on the left to meet our sponsors and to enter in some very exciting giveaways. So without further ado, I'm pleased to introduce Manasi. Manasi is the founder and CEO of Verta, and MIT spinoff that is building an open core MLOps platform for the full ML lifecycle. That is enabling engineers to robustly take trained ML models through the end-to-end cycle, including versioning, packaging, releasing, operations, and monitoring. Verta grew out of Manasi's PhD work at MIT on ModelDB, the first open source model management systems deployed at Fortune 500 companies. Previously, Manasi worked on feed ranking at Twitter and dynamic ad targeting at Google. Manasi has spoken at several top research as well as industrial conferences such as Strata, O'Reilly, SIGMOD, VLDB, Spark Summit, as well as Anaconda Con, and has authored a course on model management. So welcome, Manasi, and over to you.
Hi there, everyone. Thank you for the introduction, Faraz. Really appreciate the very cogent bio. I think that will save me a bit of time as I go through my slides. So I'm going to transition shortly to my slides. Xfinity is having an outage in my area, and so I'm going to turn off my video during the duration of the talk so that hopefully the slides come through, and then I'll be back on video for the tail end where I'm taking questions. So let me get started. I'll go ahead and share my screen so folks can follow along. And that. Okay, wonderful. All right, so welcome everybody right now to attend this talk on model monitoring. I'll be talking about why you need model monitoring, what it is, how can you accomplish it. This talk will be sort of high level on principles. I won't go super deep into system architectures. I have a couple of backup slides in case people are interested in how, in particular, we have designed some of our systems for model monitoring. If there is interest in that, I'm happy to take that on during the Q&A session. But I'll cover the basics on why and what are the key things that one needs to consider when they're monitoring models. So let me start off with a bit about me and Verta. As was mentioned in the introduction, I have a super technical background. Verta, the founded, came out of my PhD thesis at MIT. This was model management, or experiment management, as it's now called, and debugging of models. We built the first open source modern model management system, which is ModelDB. And I had the opportunity to also work on these models in production, have a sense of what it takes to keep models functional as they're used day in and day out. A bit about Verta. As again mentioned before, we are a machine learning infrastructure company. We focus specifically on operations. So everything that happens once a model is trained, whether it's documenting the model, sharing the model, packaging it, running it as and of course, monitoring it to make sure that it's actually functioning as expected. And we run models and we monitor models for a variety of companies. Find me on Twitter or LinkedIn or email, and happy to chat more about that. So what will we cover today? I'll be covering three big areas: why model monitoring, what is model monitoring, and how do you monitor your models. I'll leave you with some ideas on what are the things to consider as you're building such a system or considering options for such a system. If time permits, then also go through an architecture. All right, so let's get started with why model monitoring. We're all at ML Ops world, so we can agree that ML models are used across all functions. I have picked a few examples from the financial sector because that's where typically it's most obvious when you're losing money or making money. Few examples are robo-advisories, it's fraud protection, transaction monitoring, making lending decisions, RPA, robotic process automation. Anywhere that there is either complex data involved or there is a repeatable process, that's a prime use case for applying an ML model. And so we're seeing it more and more being used across the board. The challenge is, as we know, models fail kind of all the time, often unexpectedly and often silently. Models, when we build them, are built to work on a certain kind of data. Often when they are used in a different setting, they don't work. For example, the UK passport checker had significantly poor performance for dark-skinned women. We've had that in the US too, where Google searches produced really questionable images for folks of different ethnicities and races. The one in the middle, which is robots are now making decisions on, robots is a strong word, ML models are making decisions on where and how money should be invested. And when people lose money, they're going to sue you because your AI didn't do the right thing. I'll cover this one in a bit more detail in just a couple of slides. The coronavirus, as we all know, the pandemic really shifted a lot of market dynamics. And so in this case, the lending model stopped working. We'll touch upon that. The one that I think is very front and center in terms of how models can be biased towards a particular set of individuals is also the Apple Card, where the lending lines that were extended to women were way lower than those extended to men. And the funny thing here was it actually took a social media storm in order for the developers of the models to figure out, heck, this was actually happening. So this is all to show that these models are running pretty key parts of our businesses, and they actually fail a lot. The challenge is right now they're failing silently and unexpectedly, and so it takes either someone suing a company or a media article or social media mention for us to actually realize that these models are failing and we need to take action. So should we be surprised that these models are failing? My view, and the view that we take at Verta too, is no, these models you should expect the models to fail because they're built on a set of data that's not always accurate representation of the real world. So if we look at why models fail, and I'm going to put in a few links below, these are papers that I think do a great job of explaining some of the challenges. The first one that we are hopefully all aware of is that train and test data is frequently different. So here on the left side, these are pathology images from different hospitals. The training set, validation set kind of looks similar. When you get to the test set, even visually, you can tell that the stains are different. The way that these cells look is also different. And that's just a side effect of how this hospital might be processing slides, specimens. What are their lab protocols for actually doing pathology? So it's not something that we can control, but we're always going to be faced with data that we haven't seen before. This other one on the right is an example of satellite imagery. Depending on the country you're looking at, the thing that is a shopping mall in the Americas is probably going to be quite different from a shopping mall or a multi-unit residential in Africa, in Europe, and so on. And so if you train something in the Americas and then you want to use them in Africa or even in Europe, you're going to have a pretty hard time. And that's why when we actually start using models in production, we find out that they don't work as expected. So that's just one of them. The second one, getting a bit technical here, is that the model is supposed to capture a specific data generating process. But data generating processes change. This can be because geopolitical events, pandemics really shift the way that some of our key variables function. In the coronavirus case, as you have probably read, our credit score, a population in the US, actually went up. And this was because of the loan forgiveness. It was also because of incentives that different banks and institutions put into place so that consumers could keep up their spending. The challenge was that all of our models that are used for lending depend on the FICO score. And suddenly, as the underlying processes changed, the models for lending stopped being effective. On the right side here is another example. This is from a hospital readmissions model. So in this case, a readmissions model was built based on data from one hospital. It was deployed to that hospital and others, and the model stopped working a couple of months after it was deployed. And you can imagine that months, if not years, actually went into building and validating the model, only for it to stop working very soon after that. And the author of that model notes why some of these things happened. And it's systematic changes, such as maybe the hospital started taking insurance, a different kind of insurance. And so the people or the demographics who went to the ER changed. As they started running test results from a different lab, that meant that the data distributions again changed. So the underlying data generating processes that we're trying to model can also change a lot. And then it's no surprise that our model is actually going to fail. A few other examples of this happening in action are as follows. There are bugs in our models in our code. So very recently, Facebook's ads started banning ads for struggling businesses. And it was everything from very innocuous sort of beeswax products. It was things that looked like cryptocurrency, but were not cryptocurrency. And one of the founders of this ad company explained it to his customer. Turned up the AI, like something changed in the AI, and suddenly everything was getting shut down. This may have been an error in their code. This might have been a regex, which was more stringent than it needed to be. Things like that. But bugs happen, errors happen, and this has serious consequences on the people using the systems, such as these ad bidding systems. There's two more reasons that are happening more frequently these days. One is that ML models are increasingly used by non-experts and in unexpected ways. So democratization of AI is a good thing in general. The challenge is that if the person who's using the model is not the person who developed it, then they are less aware of the constraints within which the model should be used, what kind of data, what kind of assumptions. And this was one of the quotes from a team that we work with, where science team is building models and then developers use them, and developers have minimal ML expertise. And so they have a hard time figuring out if a model is failing and what the failure modes might be. And the final one I'll mention here for why models fail is that a lot of the deep learning models are still brittle to adversarial attacks. So if a bad actor wanted to make your model fail, they can probably find a way to do that. And so our modeling techniques are getting better, but this is something that is a reality. It exists in antivirus software. It exists in cybersecurity. We can expect it to exist also in ML models going forward. So the sum total of all of this is to say ML models fail, and they will fail. Instead of expecting our ML models to function correctly all the time, a more defensive and pragmatic approach is to actually start checking your models to make sure that they are working as expected. And if they're not working as expected, then take action. So the key step here is actually start looking at your models, start monitoring them. So hopefully that gives you a sense of why model monitoring. Next, I'll cover what I mean by model monitoring and what are the challenges or things you need to consider when we're talking about model monitoring. All right. This is probably a throwaway slide, but I think it makes the point very clearly. Like, model monitoring is being used in the community in a variety of ways. But if you go back to the basics, when you say you're monitoring something, you're checking or observing the quality or the progress of something over time. Think about a air quality monitor, think about a baby monitor, think about your system monitoring like APM. You're looking at a measure periodically and you're seeing if that measure is doing something like. So as before, then model monitoring for us means observe and check the quality of results that are produced by a model over time. And I'm highlighting quality of results here as well as over time for two specific reasons that I'll get into very shortly. But note that this doesn't have to do with latency throughput. In our sort of mental model, those are more model service health. That is less to do with the behavior of the model, but more about the software that is going, that's actually delivering that model to you. So when we say model monitoring, it's about the quality of results that are being produced by the model. Now, why is this challenging? If you think about air quality monitoring as a parallel, you know exactly what to measure. You can look at the particulate matter sample, measure it in a super fine weighing scale, I guess, in order to figure out what's going on there. However, when you think about models, the quality of models depends heavily on ground truth. The only way for you to know if a model is working as expected is going to be if you get ground truth. The challenge is twofold. One is ground truth is usually not available or not available right away. So ad click scenario, maybe you're doing retargeting. You might have shown an ad. It's going to take a little while for you to get feedback back saying, did the user click on the ad? Because you might give them 30 days to see if they actually clicked on something. There might be a third party involved. There's a lot of details there that impact how soon you can get the ground truth. The other challenge is that not all of your data points will be labeled. For example, suppose you're making image classification predictions because you have a self-driving car startup. You're not going to be able to label every frame in your video. You're going to take a subset of those frames and you're going to send them to a data labeling company to label. And so by default, your ground truth is going to be patchy. It's going to be delayed, and hopefully you get it, if at all you can. And as a result, just knowing the quality of your model results is super challenging. This doesn't even cover what are the right proxies. So sometimes your best proxy is, if you're doing, say, spam detection, your best proxy is how many users file complaints. Now, that's one of the worst indicators you can have if you're trying to build a self-learning system, but that is what we have to work with. And so the problem of monitoring the model quality actually reduces or forces us to look at proxies for the model quality. And I'll go into a lot of detail on what these measures can be. But at a first pass, is the input of the model changing? Is the featureized data changing? This could be your embeddings. This could be your n-grams. It could be some other distribution that you're computing. And you're also looking at the output. You could be looking at outliers. So in absence of this golden sort of sample or golden metric of quality, we're going to use all kinds of proxies that we can come up with in order to get a heuristic on model quality. So I'll go into the exact metrics that one can use in just a couple of slides, but making the point here that because ground truth is so hard to obtain, we end up using proxies here. So why does over time? In the definition of model monitoring, I mentioned that over time is super key. Again, this goes back to model was trained on a snapshot of data. So suppose the model was trained on time step 1, and you're doing shape classification. Most of these are rectangles. There's one triangle. You probably can get by with a model for rectangle selection or shape classification. Now, as time goes by, maybe there are more triangles in your data set. This might be different kinds of customers. This can be different kinds of content that you're seeing. Suddenly, your model accuracy is going to degrade because you haven't seen these before. Consider another variation, which is the color of these things changes, and you were expecting it to only be purple. Now your model is going to suffer because the purpleness of your shapes has actually been built. Going further along, maybe there are circles that get introduced in your data set. And at the very extreme, maybe it's not these outlines anymore. These are filled shapes. Sometimes I can also make your problem easier. Sometimes you'll look at making the point that the model that was built for this data set is not going to work for this other one. Over time, your model is going to see very different kinds of data. And so doing this repeatedly over time is super important, unlike in software, where if you write software today, it's going to more or less work even a year from now. Definitely not the case for models. All right. So hopefully that laid the groundwork for what is model monitoring. Next, I'm going to spend a bit of time talking about how to monitor your models and getting into some of the metrics that we found to be very useful in computing when monitoring your models. So when you think about monitoring a model or a data pipeline, there's three things that we think about. One is, what do you want to measure over what time window? This could be a distribution, missing values, and so on. I'll talk through that. You're measuring something. The next thing is, how do you detect changes in the measurement? So often these are not numeric values that we're measuring. These are complex data structures or distributions. How do we detect changes? And the third one, which is super key, is also, how do we know when a change merits attention? How do we know that it's what is the right p-value to set, and so on? So let's go into this in a bit of detail. So what do you want to measure? Depending on the type of model that you're building, the kind of data that you're working with, the things you measure end up being very, very different. So if you have model output, the things that you might want to look at are class distributions. Regression setting, you might care about the average prediction that is made. If you have ground truth, you're in luck, and you want to do things like F1, AUC, precision recall, whatever is appropriate in your case. That's for the output. These three columns are related to the input that are talking about. If you have tabular data, you want to look at the continuous distributions, the categorical distributions, quartile statistics, missing values, frequent values. So there's a host of these that you can measure and build. I'm listing the ones that we found most useful. And we'd love to hear in the Q&A as well as in the chat what you found useful in your particular setting. For NLP, there's tokens, there's n-grams, there's embeddings, and then your typical distributions. For images, again, embeddings end up being a pretty key way to figure out if an image fits into existing data that you've seen, or it's very different. So here's a few things that you can measure. There are great libraries, scikit-learn, PyTorch, TensorFlow. They're great for computing some of these things if you can take care of storing, visualizing them downstream. The other part here that's crucial is the frequency of measurement. If you have a time-varying problem, for example, you might want to compute at Twitter. We were predicting the likelihood of you clicking on a tweet, liking it, and so on. Depending on the type of model, it made sense to compute metrics daily, sometimes for weekly. Sometimes it was a rolling average. And so depending on your particular problem setup, the frequency of measurement also is super key. And then note that natural variability might exist. There are weekly sort of changes that happen. There are monthly changes, and something that you want to account for. So the next one is how to detect changes. This has to do with, I'm measuring these things. Now I want to know if there's a difference. And there is a host of statistical tests that you can use here. I'm looking at a paper that I think does a good job of laying them out. Your statistic, the chi-squared, because models are high dimensional, univariate versus multivariate testing becomes really important. This paper makes a case for dimensionality reduction, which we found to be very useful as well. And then finally, you have a lot of outlier detection algorithms, whether it's just 3 standard deviations away or something more complicated where you're measuring the distance between one data point and a distribution. Depending on your particular data type, you will pick an outlier detection algorithm that's a good fit for it. And then the final one here is, you know what you're measuring, you know how to measure change, what merits attention. This is where getting very fine-grained on what p-value do I care about. If you're using, say, Earth movers distance, cosine distance, what do those things mean? Is 0.2 something acceptable? Is that a cause to just stop everything and pay attention to a model? That is an intuition that needs to be developed over time, or a system can also recommend these thresholds over time. And just noting here that as we start monitoring models, the alert fatigue that we've seen in whether it's healthcare or DevOps, we're going to see that here too. And so defining what change actually merits attention is a key problem that I know we've spent a lot of time kind of trying to take on head on. So those were the key, I would say, the key 3 things that you want to think about. When you get into implementation, there's a few things to be aware of. You want a system that can scale. And someone actually mentioned ad hoc pipelines, which I think are great for the offline processing and a great way to deal with scale. The question that still remains in our experience is what to do with live. If you're making live predictions, is it okay to turn that into a batch job? So it depends on how quickly you want to react. There are pipeline jungles. ML model is only one part of your full system. And so once you have monitoring information from all parts of your pipeline, making sense of it becomes a lot harder. Accessibility and customization. So tooling options, I would say build your own. And I think we've seen a lot of great examples of this. It was funny, the ad hoc pipelines is something that we've seen a lot in the field. And depending on the particular setting, I think it works well. It's good for, in our experience, it's good for few models, batch predictions, and also assumes a lot of data science and DevOps skill. If you go with a existing solution, we found that it's good for lots of models when you have batch and live, when you care about performance. And depending on the effort and the amount of money you want to spend on things, you can make. Whether you're building your own modeling solution, whether you're picking a solution, I would say there's 5 things that I think are important. One is a solution should tell you when your model is failing or about to fail. That's the whole point of monitoring. It can collect fancy statistics, but if it can't tell you that your model is, it hasn't served its purpose. It should also be customizable because every model is going to be unique. So you should be able to bring your own statistic, so to speak. It needs to be data science friendly versus DevOps friendly. Grafana, Kibana, great for DevOps. In our experience, not so great for data scientists who want to get their job done. It should help you in identifying the root cause. So if there's a pipeline jungle, it should help you identify this is the area that you want to be debugging or looking more into. And then finally, it should support closing the loop because ultimately you want to retrain or you want to ask for data labeling or you want to take an action depending on what the monitoring says. So that's the last piece that you should be looking at. So that's what the key areas that I wanted to cover given the short time that we have. So I'll just summarize and then switch to questions. From what we've seen, are going to continue driving key user experiences and business decisions. And model monitoring at its core is ensuring that results are consistently of high quality. That's the one thing and the only thing that a model monitoring system should be caring about. And if it's done right, it's going to identify failing models before social media or just media does. It's going to help you democratize your AI and quickly react to market changes. So with that, if you're interested, check out that link. Also, feel free to reach out to me on email or LinkedIn, and I will stop here to take questions.
Thank you so much. That's a great presentation. Thank you. We do have some questions just coming in. Just before we get into that, I just remind the attendees just to go into the poll, just to give us a good, to give us some feedback on how the session went. So the first question is from Nadine. You mentioned some monitoring tools that are more friendly to data science versus DevOps. Which tools in your experiences were more appropriate for data science?
I'll answer the opposite question in just because right now the tools are getting built. It's whether it's startups like Verta who are building it, whether it's AWS who's building similar tooling, those are very early. You know, data scientists like Tableau. The ones that we found to be not very friendly are things like Grafana, are things like Kibana. There's just the mode of operation or the kinds of queries that you need to write in order to get those two tools to work for data science. That has been pretty challenging. So I would rephrase that as to say more data tools are necessary, and they're getting built today. So hopefully in 6 months or a year, the situation will be different.
That's great, thank you. You had also mentioned that there is a gap between the teams who are building versus the teams who are monitoring. How do you bridge that gap?
Yeah, I think so. There's two aspects to that. The people who are building models versus the people who are consuming models are different. And that's where we found that a solution like a model registry can help a lot. So registry is a place where once a data scientist builds a model, they are publishing the model along with code on rather documentation on how to use the model, what are the places where the model is going to work well, and also distributions so that you can, I'm actually trying to pull up a blog post on this so that I can put it into the chat. So that you know when you're using a model, you know what are the modes in which it is supposed to be used and what might be pitfalls of using that as well. Mm-hmm. So here's a quick blog post on model registry if you think that's useful to you folks.
That's great, yeah. Also, this question just came in private. If you had any resources outside of the blog that you just shared, please do let us know as well.
Yeah, so in my, go ahead.
For model monitoring, if you had any of the resources that you want to share with the attendees.
Absolutely. So I'll throw in one that I think does a great job of providing an overview of model monitoring there. And I'll leave my email as well if folks are interested. Feel free to send me a note. And I'm happy to point to resources. I don't know how to communicate with these folks post this event. So feel free to find me after.
Yeah, so what we'll do is we'll connect with you, and then we can most certainly gather those resources and we can send it out to the attendees for sure.
Great, sounds good. And I have a few links in my slides too. I think they have some good overviews of how to manage that.
Sounds great. We do have a couple more questions if you have some time to
yeah, absolutely. Yep.
So Karthik asks, for some regulated applications in healthcare, for example, the model might be locked in for a while because getting to the ground truth can be a while. For example, if you're working on automation in clinical trials, manual authentications of outcomes can take a month. How do model monitoring work with those kinds of applications?
So this is not just in healthcare, but everywhere. That was what we learned is you should assume that you're not going to have ground truth in most cases. And that's where, in our experience, model monitoring is very essential because you're not going to know whether something works or not. That's where looking at the distributions of your input data, your intermediate data, your missing values, your most frequent values, and so on becomes super, super key. On my slide, I think I'm sharing slides after, right, for us, in case people want to go
yes,
check them out. Okay, perfect. So then one of those slides talks about, depending on your data types, what should you be measuring? So if you're in healthcare and you're looking at clinical notes, it's NLP metrics that you should be tracking, and there's a few metrics there. In an ideal setting, what's happening is every time that you make a prediction, you're computing these statistics, you're storing them to a database, and then you are running alerting or analytics on top of it. So this does not depend on ground truth. This just depends on your input data and intermediate data or process data. that your model cares about.
Sounds great. We've also got another question from Rajiv.
Mhm.
Are ML products uses rules or models or a combination? So we
Mhm.
track which prediction is done by who. This is a internal API contract. If we have to integrate with Verta, for example, is there an API contract / interface or a standard that you have found to work with ops monitoring between model interference and ops?
So the way that we do this in our system is anytime that a model makes a prediction, that model prediction is also piped to the monitoring system, typically done asynchronously. And so I mentioned registry earlier. We deploy models that have been registered in the system that have a input and output contract. And so the system automatically knows what it should be looking for. So there is an age value, for example, it knows how to unpack the IO so that it can do monitoring on it. And so think about it as shadowing traffic to your monitoring system almost.
Sounds great.
And happy to answer follow-ups on that.
Mm-hmm. Sounds great. Thank you. And I think that's all the questions we have. Thank you once again for a very informative presentation. Thank you.
No problem. Feel free to reach out, folks. This is something that I spend a lot of time thinking about, so happy to chat. Appreciate it.
Thanks,
All right.
everyone.
Thank you all. Bye.